Hey guys, welcome back to chapter 17. In this video, I'm going to work another example of calculating the pH of a buffer using ice tables. So here's our problem. Calculate the pH of a buffer solution that is 0.25 molar HCHO2 and 0.5 molar NaCHO2. Go ahead and pause the video, see how far you can get into this, and then I'll catch up with you. All right, so step one, write a balanced equation. So here I'm going to see a weak acid. So how to identify it as a weak acid? Well, first I see this hydrogen in the front, so that tells me that it's an acid. It's not one of the big five, so I know that it must be weak. So HCHO2 reacts with water. If it's an acid, that means it's a proton donor. So it's going to donate that front proton to give us its conjugate base. And then water in this case must be acting as a base, accepting that proton. So we get hydronium on the other side. And we see this common ion here. So we see the salt. And again, sodium is neutral, so it's just going to spectate, and we see that ion. So that's write a balanced chemical equation. Next step is to set up an ice table. So let me rewrite my equation. Okay, let's do our ice table. Okay, and click back for just a second. So for this one, we see the initial concentration of the weak acid is going to be 0.25 molar. The initial concentration of the weak or the conjugate base is going to be 0.5 molar. And again, no mention of the hydronium, so we're going to assume that's 0. And then the one other piece of information that I should have included in the problem, but I will always give you, is going to be the Ka value. So Ka value for this particular equation is 1.8 times 10 to the -4th. Okay. All right, so looking at this ice table, only way for hydronium to go is up, which means the conjugate base is also going to go up, which means our weak acid is going to go down. So we're going to have 0.25 minus x, 0.5 plus x, and x. Okay. So let's do our Ka equation. So 1.8 times 10 to the -4th. Concentration of our products at equilibrium is going to be 0.5 plus x and x. And concentration of our reactants is 0.25 minus x. Again, we're going to assume x is small, so x being subtracted, we can get rid of that. And 0.5 plus x, so adding a very small number is not going to change it much either. So assuming x is small, that is going to clean this up to the following. 0.5x on top, 0.25 on the bottom. Okay. So now we just need to solve for x. So the first thing I'm going to do is multiply by 0.25. So those cancel. Multiply this side by 0.25 as well. So we've got 1.8 times 10 to the -4th times 0.25 So over here, we've got 4.5 times 10 to the negative fifth, and that equals 0.5x. So we're going to divide by 0.5 to get x by itself. So x equals, 4.5 times 10 to the negative fifth divided by 0.5, and we get 9 times 10 to the negative fifth. So remember, what is x? X is the hydronium concentration. So 9 times 10 to the negative fifth. So pH is going to be the negative log. Oh, not 9.5, just 9. So pH equals negative log of that answer, and I get 4.04. So that is your answer. I hope you guys found this helpful.